Good morning dear students, welcome back. I am your physics professor Dr. Nagaraj. So I am going to teach quantum computation for engineering students. This is part of the engineering physics syllabus VTU, and of course it is going to be useful even for the other university students also. My advice, please watch my videos in the order like part 1, part 2, part 3, part 4, part 5, part 6 like that. Okay, so now in the previous part I was talking about representation of qubits using block sphere and also using vector space, how to represent qubits, and also I mentioned what is that 0 state and 1 state, physical meaning of qubit. Just a small recap. 0th state is called as ket 0, it is represented by 1 0, and then ket 1 is represented as 0 and 1. They are column vectors. Okay, column vectors 1 0 and 0 1. Well, how to represent the superposed state? Superposed state is nothing but ket psi, that is equal to alpha into ket 0 plus beta into ket 1, where alpha and beta are called probability amplitudes, and according to normalization condition, modulus of alpha square plus modulus of beta square must be equal to 1. See, there are only two possibilities, therefore we have two probability amplitudes, and alpha can vary from 0 to 1, beta can vary from 0 to 1. Okay, and we discussed how to represent this superposed state in block sphere. Just recap of the previous video. Now let us proceed further with what is called multi-qubits. In multi-qubits, we have interaction between 0 and 1, or 1 and 0, and 0 and 0, and 1 and 1, like that. So there will be interaction. So after interaction, what is going to be the column vector? What will be the new state? See, remember, the 0 and 1 are called basis states, and whatever you get after the interaction, okay, they are not basis, they are not fundamental. Like x, y, z, they are fundamental. After combining x and y, y and z, z and x, it's not going to be a fundamental. It is nothing but vector space, part of the vector space. It is called state vector. Okay, so this is basis vector, they are called state vectors. State vectors are consisting of multiples, or the combinations of zeros and ones. So before going with the combination of 0 and 1, let me teach you how to calculate the product of two kits or two column vectors. How to find the product of two column vectors. The product of two column vectors is also called as a tensor product. So I will teach you a little bit about tensor product. What is this tensor product? How to find a tensor product? Let me consider two vectors. Let us say u, it is having a member x1 y1, and v, and it is having x2 y2. Now I want to find the product of these two. Dear students, when I say product, it is not simply multiplication sign. See, in vectors the product carries totally different meaning. Similarly, here in the case of vector space, we have what is called tensor product. How to find, what is its meaning, we shall try to find out now. And remember, tensor product is also called as Kronecker product. So another name is Kronecker product. How to go ahead? See, u and v multiplication, that is tensor product, is represented like this: u cross with circle, this is a tensor product symbol, into v. That is equal to, so here comes the method. First u cross v, u first element is x1, next element is y1. Okay na? Next x1 I have to multiply with x2 and y2. See, I am multiplying u on v. If you do v on u, then you should write x2 and y2. This will be x1 y1, this will be x1 y1. Anyway, it is now x2 y2. So I suggest you try v cross u also. V tensor product u also. Okay, let us go ahead. What it will happen, that is equal to x1 into x2, that is x1 x2. Okay, next x1 into y2, that means x1 y2. Suppose if you have v cross u, what you will have, it is x2 into x1, that is x1 x2 becomes x2 into x1, that's all. So just interchange. There will be no change in the overall meaning. What I mean to say, u tensor product v is equal to v tensor product u, like that. Okay, let me proceed. y1 x2 into y1 y2. Okay, so totally how many elements we are going to get? Yes, 1 2 3 4. So it is a 4-dimension column vector. vector when you have two vectors overlapping or interacting, and these two vectors purposefully I have taken two dimension because my 0 ket and 1 ket are having only two elements in their respective column vectors. Therefore I took x1 y1, x2 y2. Is that clear? Yes, sir. If there are three vectors like u, v, w, or x, y, z, or a, b, c, how to find? Yes, that also I will teach. Okay, before that, let me come back to this. If there are two vectors with two dimension, we deal with only two dimension, not 3 dimension, 4 dimension, because for us only two states are required: down state, up state, ground state, excited state, spin up, spin down, left, right, like that. Okay, only two. Therefore all the column vectors will be having only two elements in the column vector. Okay, so if there are two elements and two vectors, I am going to get 4. Right, how it is, or how to write this? This can be written as 2 to the power of n, that is 2 to the power of 2, that is going to be 2 to the power of 4. 2 to the power of 2, that is 4. Okay, suppose if there are three vectors, let me take three vectors like vector A, ket A, it is having a0, a1, two members. Ket B having again two members, b0, b1, and ket C having two members, c0, c1. What it is going to be? It is ABC or AB and then C, or C and AB. First I will do AB. So like this, that means this is nothing but U cross V. That means it is nothing but, this is nothing but A cross B. I should call this as tensor product, not cross. A tensor product B. That is going to be, straight away I will write A0 B0, like x1 x2, x1 x2, x1 x2. Next x1 y2, that means x1 y2, that means a0 b1, correct? X1 x2, x1 y2. Next x2 y1, okay, or y1 x2. Okay, this is something like x1, this is something like y1, this is something like x2, this is something like y2. Okay, like that. Okay, now x1 x2, x1 y2. Next y1 x2, that is a1 b0. Next y1 y2, that is a1 b1. Okay, so this I am going to generate when I go for AB. Suppose if I now go for C tensor product AB, you know what it will be? Yes, it will be, yes, it is like this. C, that is C0, this whole thing, that is A0 B0, A0 B1, A1 B1. Okay, this full, and then C0 over. Next C1 into just repetition of the same. Right, just repetition of the same. Then if you do the calculation, what will be the final answer? I write the final answer here. Yes, it is C0 A0 B0. It is C0 A0 B0. Like that you keep on writing C0 A0 B1, C0 A0 B1. Okay, now tell me how many elements you are going to get. Yes, 1, 2, 3, 4. That is C0 A0 B0, C0 A0 B1, C0 A1 B0, C0 A1 B0. Right, I hope you are following. Next C0 A1 B1, C0 A1 B1. Correct? Next, so 4 elements are generated with C0. Now you just replace C0 by C1, rest everything remains as it is. So C1 A0 B0, C1 A0 B1, C1 A1 B0, C1 A1 B1. So this column you are going to generate. Tell me how many elements are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 when you have 3 state vectors. Sorry, 3 basis vectors. So when 3 vectors superpose, overlap, or do whatever they want, then you are going to generate 8 elements in the column vector. That is what I said here. 2 to the power of 2 is 4. This is nothing but 2 to the power of 3. So that is nothing but 8. Like that, if there are n number of qubits, when n number of qubits interact, you are going to get 2 to the power of n. 2 to the power of n. Understood? So that's all. So this is about the tensor product. This is a general expression. So instead of taking u and v arbitrarily, A and B and C arbitrarily, let me take 0 and 1 only. Suppose if 0 and 0 interact, what is going to happen? Let us see what is going to happen. If 0 and 0 interact, what will happen? Yes, 0, I write it as same way, this way. I write it as u, that is was 1 0 1 0. Okay, 0 is 1 0, once again 1 0. That means 1 0, that is for this 0. Next 0, I write 1 0 and again 1 0. Got it? Please check this, compare this with this column vector. Simplify. What will happen? If you simplify, I just erase this part. Let us see what will happen. Now 1 into 1, it is 1 is equal to 1. 1 into 0 is equal to 0. Correct? Next 0 into 1 is 0. 0 into 0, yes, it is 0. Correct? Understood? That means 0 0, when 2 0 qubits interact, you are going to generate this column vector. 0 0, when they interact using tensor product, I can show that this column vector will be having 4 elements, out of which only first member is 1, remaining are zeros. Clear? Like this you try. Another one, which one? 0 1 state, that is equal to 0, that is 1 and 0. Next 1 is here, 0 1, that is 0 1, and then again 0 1. Well, I write the result over here. 1 into 0 0, 1 into 1 1, 0 into 0 0, 0 into 0 0. So this is the element I am going to generate when 0 operates on 1. Suppose 1 operates on 0, that means instead of writing this, if I go for 1 0 ket, does it going to be the same way? No, definitely it is not so. We will do that also. 1 means this one, 0 and 1. So it is 0 and 1. Next 0 means this one, 1 0. So I write 1 0 here, again 1 0 here, and finally let us see what will happen. That is equal to 0 into 1 0, 0 into 0 0, 1 into 1 1, 1 into 0 0. So we will have this column. Please check, please check. Here the column is 1 in the first place, that is for 0 0 interaction. Here 1 is in the second place, that is for 0 1 interaction. And here 1 is in the third place for 1 0 interaction. Can you guess the next one? Next one, what if 1 1 interact? Yes, you are correct. Definitely you are going to get 0 0 0 1. Clear? See, when 2 qubits interact, you will have 4 elements. So 2 qubits superimpose gives you 4-dimensional column vector. When 3 qubits superimpose, 8-dimensional column vector. When it is single qubit, 2-dimensional column vector. So we can say, in fact, this is 2 to the power of 1, this is 2 to the power of 2, this is 2 to the power of 2, this is 2 to the power of 3, and so on. Are you following now? So this is the way of representing the qubits. Okay, I have 0 0, 1 0, 0 1, 1 1. Suppose if I have only 0 and 1, I write the superposed state in this manner. Suppose if I have this type of interaction, how to write psi? That I will tell you now. 0 1 or 1 0, 1 1 or 0 0. Let me summarize them. 0 0 will be 1 followed by 3 zeros. Okay. 0 1 will be 0 1 followed by 2 zeros. Next, 1 0 will be 2 zeros, 1 and again last one is 0. And finally 1 1 is equal to 0 0 0 1. So these are the basis vectors. Now I call them as basis vectors. Actually they are not basis vectors, multiple qubits. They are called multiple qubits. Okay. Now if they superimpose, if they interact, what is going to be this psi? How to write the final value? Dear students, if there are two states, there will be two probability amplitudes. If there are four states, how many probability amplitudes will be there? Yes, you are correct. There will be 4 probability amplitudes, and therefore that resultant will be psi. Okay, I write it here. Psi ket is equal to, I now take alpha. Instead of taking alpha beta, I take alpha only. Alpha for 0 0 state into 0 0 ket plus alpha for 0 1 state into 0 1 ket plus alpha for 1 0 state into 1 0 ket plus alpha into 1 1 state into 1 1 ket. This way we can write. And in this formula, if alpha and beta are the probability amplitudes and their modulus square is equal to 1, and why not in this case? It is applicable even here also. What I mean to say, here also we can write modulus of alpha 0 0 square plus modulus of alpha 0 1 square plus modulus of alpha 1 0 square plus modulus of alpha 1 1 square must be equal to 1. There is no compromise on this. And that means alphas can take any value, but maximum is 1 and all put together is equal to 1. By chance, if this is 1, rest everything are 0 and so on. Okay. In fact, in the previous video, we came to know that when alpha is 1 by root 2, beta is also 1 by root 2. That means the probability of finding the qubit in spin up state is 50%, spin down state also 50%. Okay, so equal probability. Suppose if you take here also equal probability, what might be the alpha 0 0 0 1 1 0 values? Can you guess? Yes sir, it is correct. It is nothing but 1 by 4 1 by 4 1 by 4 1 by 4 square. Of course alpha 0 0 is 1 by root 4. We can show that it is 1 by root 4. When you square it, this is going to be 1 by 4, this is also going to be 1 by 4, and this and all put together it is 4 times 1 by 4 must be equal to 1. So this way we can express the superposed state in case of multiple qubits. So this is a superposed state for single qubit, this is a superposed state for multiple qubits. I hope you got the meaning of multiple qubits concept. Dear students, now with this knowledge, let us move on to next topic. Before I go to the next topic, let me mention the properties of qubits. Actually, I was supposed to mention the properties in the beginning itself. Number 1, qubits are making use of the particle behavior, particles like electrons and photons behavior, like spin up, spin down, polarization or ground state, excited state, etc. Next, qubits can exist either in the 0 state or in the 1 state or linear combination of 0 and 1, anywhere from 0 to 1. So multiple combinations they can have. See, I am just summarizing whatever we discussed so far. So 0 to 1, any state it can have. Suppose if there are 2 to the power of n operations, all 2 to the power of n operations we get. Okay, so that means 0 to n minus 1, 0 to n minus 1, including 0. N terms means 0 to n minus 1. All the options, like if you have 2 to the power of 4, 2 to the power of 4 is nothing but 16. That means 1 to 16 or 0 to 15, everything we can have. Okay, so like that, all possible combinations, all outputs are possible. And finally, when the qubits give the information, finally they will return back to either 0 state or 1 state. They return back to 0 state or 1 state. And another special property of the qubit is they are going to entangle each other. Entanglement is a totally different phenomena. Einstein called it as a spooky action. I will explain entanglement in detail in some other video. It requires a lot of time, and also some examples I have to give. So this is not the right place to explain entanglement. I take up in the next video or subsequent videos. So these are all the properties of qubits. I repeat, qubits make use of particle properties like electron spin or electrons energy, etc. Qubits exist in the 0 and 1 state, and of course they are the members of vector space, so they can be represented by column vectors. Next, qubits can have any state between 0 and 1. This is called superposition. And once the qubits give information, they return back to either 0 state or 1 state. Okay, and qubits, another special property is they exhibit what is called quantum entanglement. And finally, qubits can be expressed in a spherical form or in a diagram called block sphere. Okay, so that's all about the properties of qubits. Well, back to this. See, this is 2 qubits. This is combination of 2 qubits. So totally we have 4 probabilities. Like that, you can have any number of qubits. I already wrote one column vector here, no, which consisted of 8 elements. Like that, you can have any number of any number of qubits 0 to n. Okay, n qubit, but each qubit is having 2 elements only. 2 elements only. 1 0 or 0 1 ashtene, not more than that. In that case, this superposition, we can write it as, superposition can be written as sigma, okay, alpha, like alpha suffix x, where x can take any value from 0 to 2 to the power of n minus 1, not 2 to the power of n. Suppose if you take x is equal to 1, then I can write 2 to the power of n into ket x. This is the simplified or general form of multiple states or superposed states. Clear? So x can be any value from 0 to n minus 1. So this is about representation of qubit, superposition of qubits, and then calculation of the superposition or multiple qubits using a tensor product. Okay, so with this I stop this video here. I come back to you with a few more details in my next video. I'm going to talk about properties of Dirac notations, and there is one more notation called Bragg vector. Okay, so far we were talking about ket. What is this Bragg? Very simple. You all know this is nothing but bracket. So you break this, divide this portion. We write it like this. This is called half of the bracket, that is ket. This portion we write like this. This is first half of the bracket, that is nothing but Bragg. So Bragg plus ket, bracket. So bracket vectors are Dirac notations. Ket is already now familiar to us. Ket we write like this. 0 ket or 1 ket. 0 ket is 1 0 column vector. This also 0 1 column vector. Suppose if I write this in the Bragg form, how to write? Like this we have to write the Bragg. Corresponding, it is 1 0. Come on, tell me what it is. Yes, it is row vector. Similarly, this how to write? We write it as 0 1. This is also row vector. So this is ket vector, this is Bragg vector. Ket vectors are represented in column matrix form. Bragg vectors are represented in row matrix form. So column row can be multiplied, column can be added, column matte row can be added. So all these things demand proper knowledge of matrix. Operators, like there are various operators: unitary operator, identity operator, null operator, inverse operator, complex conjugate, all these things. If not all, some of them are already known to you, so I make use of those things and I will explain the remaining concepts of quantum computation. Okay, I hope you are getting the essence of quantum computation. I don't think you are finding it very difficult now. Okay, so here onwards it is full of mathematics only. I will try my level best to make things as simple as possible. Please stay with me and share your comments, and also subscribe to my channel, and share the channel link to your friends also. Okay, thank you very much.